Thank you so much for coming, Manan. I put out a call on Math Twitter. That's how we have interacted with each other in the past. Manan comes up with so many interesting things and math comics and interesting blog posts that I've been following him for quite a time now. But he was willing to come on and talk about kind of computational approach to derivatives. So would you be willing to introduce yourselves
Yeah,
to my students? Yeah.
yeah. Hello. My name is Manan Shah. As John mentioned, how we know each other is through Math Twitter, and it's been a fun way to meet other mathematicians. Outside of my blog and general piano and random drawings I may do, I do work in the industry as a mathematician. I head up an analytics team, and in the past, I've run data science teams. And have been in various industries from gaming and gambling to video ad tech to just video technology. And we're here to talk about derivatives.
Excellent. And so he showed me on Twitter some code that he whipped up, and he's going to show that to us now.
Cool. All right. We're on a separate screen for that. So the bulk of my job, my day job, if you would, often involves writing code and computing things. Outside of that, we do have to use our mathematics and the calculus that we learn in various ways, but often in a computational way. So what you're seeing here is what's called a Python notebook. It's in something called Jupyter, and that's just a good visual aid for you to run Python code sort of seamlessly in real time, and you can sort of interact with it as much as possible. And then depending on the various libraries you have installed, the interactions can be more dynamic or more static, but you can still sort of play with your variables, if you would.
Yeah, and if my students keep on with math, they'll definitely see this in some of their courses as it comes. They use Sage notebooks and Google Colab to host Python, and
yeah,
or if they're kind of going into computer science, we have mathematics courses specifically to support that, discrete structures and things like that.
Yeah, it's pretty much a hiring requirement for anyone at this point. If they're looking to start analyst roles or data science roles in industry that have at least a background in R or Python.
Yeah. All right. So what does this program do?
All right. So here, what I'd set up for us was just a Python notebook that will help us compute derivatives numerically. And we can take a look at what some of the pitfalls are with numerical computation. But the idea here is there's sort of like a calculus approach to computing derivatives, and that is the way the course progresses in a theoretical way. But that theory is based on how we take our slopes from say like an algebra class where you had that equation of a line y equals mx plus b, and your m was your slope. And when you had just a line y equals mx plus b, you could always read off that slope as a number. But here what we want to do is when we have functions that are not just simple lines, but maybe they have some curves in them, or they have some change in direction, we still are interested in slope at various points on that curve. And the idea here is how would we find that slope on that curve as we traverse over the curve. So what we have here, these first two lines basically are importing a bunch of libraries that I might need. This function here is just a way for me to call a function that I would want to write. So in this particular case, I wrote function of x, and it would just give me back x cubed if I wanted to. And to demonstrate kind of how that works is if I did function of 3, we should get 27. And then if I wrote function of 123, If you can do that in your head, that's great, but you'll get something like this. And
Definitely out of my mental computation.
and the nice thing about Python is we can go a little nuts if we wanted to, and kind of get these big numbers. But anyway, that's the point of this function here. Now, our next function is dy dx, and John, feel free to stop me whenever it makes sense. But what we're trying to do is basically compute slopes at different points on a curve of our choosing. And the way this function works here is you have this value f, which is whatever function we want to send in. And that function could be my x cubed function. It could be sine of x. It could be just plain old x.
Yeah.
We want to know how much we should increment the function by. And we want to know over what interval we're interested in looking at the function.
Okay, so this is just working. It's not working globally.
Right.
We're kind of picking a range we want it to work on. And for the step size, you're thinking about like when we write these slope formulas, that's like the difference in x we're going to use.
Yeah. So the way this will work is if we just read through the code, we'll start at the left endpoint of the interval.
Okay.
And we're going to continue to step forward in the interval until we have exceeded the right endpoint of the interval, right? So what this is saying is, as a simple example, if my interval were 0, 1, s begins at 0. If my step size were 0.25, it would say, well, the first point in my interval is 0. The next point in my interval is going to be 0 plus 0.25, and then 0.25 plus 0.25, then 0.5 plus 0.25, and then 0.75 plus 0.25. And so it'll try to fit in as many of those step sizes as possible into the interval that you have chosen. And then from there, all we do is compute our, depending on what vocabulary we might have come across in the past, this is our slope, right? It's the change in y, which is this difference divided by the change in x. And since the change in x is always this constant step size, that's your slope wherever you move across x.
So this is analogous to kind of that f of x plus h minus f of x over
yes.
8 that they would have seen in their calculus book.
Yeah, that's right. So this part over here is just your f of x part, and then this is your f of x plus h part. And so what this function then does is it returns back to me, the user, all the x's that I used and all the slopes that I'm getting at the various x points.
Okay, so it's like a collection. For every point it samples, you're getting the slope of one of these secants, and it's returning to you kind of a list of slopes.
Yeah. So we can see it run here. And so I can pass in, let's just say a very simple function like x squared. And let's just say that I wanted to move in quarter size increments over the interval 0 to 4. And so what it will give back to me, and I will put this into two variables, x's, and we'll call these slopes. And so now we'll take a look at what our x's are. So our x's basically are the 0, the quarter, the half, the 3/4, so on and so forth. And we'll see what our slopes are. So the slopes here, and this is sort of the thing that we can do by hand just to verify if we wanted to, where this slope here of a quarter is basically saying, okay, well, I was at f of 0 and my delta h. So if we think about our formula, right, it might be easier to simply see this as our derivative formula, right? We can do f of x plus h minus f of x divided by h, right? That's our, without the limits. Right. We haven't talked about limits. So this is just
Yeah.
Um, so if we take a look at where this 0.25 comes from, well, that should be a matter of my h here is 0.25 everywhere I went. So the first thing I'm going to do is I'm going to say, well, I've got x plus a quarter squared minus x squared. And then all of this is divided by h. And so if I set my x to be equal to 0, this first point here, and I set my h to equal the 0.25, we haven't done this, so we'll see if all the computations are correct. We get 0.25.
Very nice.
And then what we can do is we can just change where our starting location was. So let's just say that our starting location is this half. So if the starting location is a half, then what I'm going to have here is 0.75 squared minus 0.5 squared, but still divided by 0.25. And here, I get my 1 1/4.
Yeah. And it's nice, even though you put in a function like x squared, so it's this parabola, the slopes have this, really pleasing pattern. They're going up by 5/10 every time, right? From 0.25 to 0.75 to, right? So they're increasing linearly.
Yeah, that's right. And I can just do one more thing just to make sure that, let's see. Okay. So what we'll do here is we'll do a simple plot of my x's against my slopes just to see what that looks like. Okay. To your point, right? Like if these are always moving up by 0.5s, that shows up right here in our function.
Right. So that is a graph, because at every x we're associating a number. Really, we made a new function.
That's right. Yep. Yeah. We basically said that our initial function x squared, wherever it was, when we were looking at this type of difference divided by this h, and we did it everywhere along its graph, we find, interestingly, a very simple and pleasing and easy to understand function.
Yeah, excellent. So so what would you want to play with next, right? So you started out with a pretty simple function.
Yeah, so we started with a simple one. Now what I do want to do is I'm going to go ahead and also just put a little plug in for having all of this stuff done in one step, right? So now that we've seen like how this mechanically works step by step, we'll just skip ahead to a general way of looking at this, where what I do here is I name my function my function of interest. So what function would you like, John? How about that?
X times cosine of x.
All right, x times cosine of x. So there's x times cosine of x, and then for display purposes, we'll just write that guy, okay? And maybe we can go over what the full period of cosine.
Sure.
From 0 to 2 pi.
Or maybe 4 pi. Could we do kind of?
We can do 4 pi. Yeah. So there's the interval 0 to 4 pi. So that'll give us 2, or maybe, well, who knows? It's x times cosine of x. So it's going to look a little bit different. And so what we're going to do is, to make this look smooth and nice, we have to actually sample this interval in enough spots, just to show what the function looks like. But we're going to, the way we did it earlier here was we picked a fixed step size of a quarter. And what I do want to show us is what happens how much this derivative, or this difference that we're talking about, this difference quotient that we're talking about, depends, and what it looks like when we change our step size. And it's not just a quarter, but it could be of varying length. So I chose step sizes of 2 units, a unit of 1, a half, a tenth, and then 10 to the negative fifth.
Excellent. So for me, that feels like it really duplicates kind of the thought process of Newton and Leibniz, right?
Yeah.
Kind of going from these different quotients that people have been computing for hundreds of years to their imagination of the kind of this infinitesimal.
That's right. Yeah, so we can make that delta H smaller and smaller and smaller.
Yeah.
And so here what we'll do is we're just going to run this. Everything else after this part is just plotting. And you'll notice that I'm calling my function dy dx. That's the function that we made up earlier, where it will take in x times cosine of x. It'll take in the step sizes that we chose, and then it'll take in the interval that we decided on. Okay.
Excellent.
And here we go. Let's take a look and see what happens. All right. So we've got a bunch of things. And should I zoom in a little bit? Maybe. Let's see. It gets a little finicky with the zoom. All right. So what the heck are we looking at?
Yeah. So that initial step size, it looks almost like just a kind of a piecewise linear.
Yeah. So that's this orange, right? It's in some sense it's poor sampling if we were thinking in terms of this derivative that we haven't yet talked about. But right, in another sense, there's nothing wrong with it. It is our secant line. It is telling me that x times cosine of x from 0 to 2 kind of changes like this orange line here, fairly flat. And then from 2 to 4, well, it's saying that just because of the way it got sampled, it's changing like this, and then there's another change like that. Yeah. This is positive, right? So, and then, or this is increasing and then it goes to positive, and this is decreasing and goes to negative eventually.
Yeah, that's actually a little surprising. You would have thought.
Yes.
Oh, I see. Yeah. So thinking about where the 0 line is, we can kind of see where it's crossing over.
Yeah. And I mean, part of this is just an issue with sampling, and also maybe just the fact that these are fairly large movements. So who knows what it's actually getting, because it had to look at this point and then this point, and then it took a look at this point and I guess this point, and maybe it should have been decreasing, but it isn't. But yeah, something's happening here for sure in terms of how it got sampled.
Although the other thing that strikes me is kind of how quickly it converges.
Yeah, so this isn't too bad, right? Like we don't really need to get very, very fine, but you do notice that there are some differences between even a step size of 1 or a step size of a half. It's right around a 1/10 where you can't tell the visual difference. And it's only because this function is fairly smooth. It doesn't have these steep movements. If it had steep movements, then a 1/10 just still might not be enough.
I imagine the kind of data that you come across could be seriously chaotic.
I would say that it's hard to even put a function to it. Yeah. So, there you do have to always either worry about where you're sampling the data or how you're sampling it or how you're conditioned. And also the data tends to be very high dimensional. So you're almost never working with f of x. You're working with f of x1, x2, x3, x4, x5, mm-hmm. up to like x500. And then you're trying to make sense of what a derivative in any one direction even means.
So but there's so much stuff about it that makes sense, right? Like that it has kind of this periodic feel like the original function did, which it feels like the slopes should be doing, but the slopes are kind of increasing in amplitude as the function kind of changes more rapidly.
Yep.
So I feel like it kind of gets at the feel really quickly.
Yeah, it does. And if you notice, if we ignore the orange to the whatever color this is, but we look at, the sharper brown or purple, depending on how it shows up on the screen, you'll notice, right here, it's about 0. The derivative is about 0. And that kind of makes sense because the function has peaked over here.
Right. Which is where we're going next. We're going to be using this idea about trying to find the zeros of the derivative.
Right.
Yeah.
Right. And so you'll also notice here where the function has reached some type of minimum, or it's about to change direction, the orange curve, is sitting on 0.
Yeah.
These are
the
nice.
function's decreasing, slope's negative, changes to increasing, it has to cross 0 in between.
Yeah, that's right. So why I like this is because it allows you to, when I remember when I was first learning calculus, this was before Python even existed, I think. So the challenge there was you had to do it on paper. And you had to write out inputs and outputs and do the delta calculations by yourself. And if you wanted to actually see what a derivative looked like, you really had to do maybe 50 of these by hand, punching it into the calculator of 0.1 steps, 0.1 steps, 0.1 steps, because these steps were too coarse and you couldn't get a sense of what the derivative ought to look like.
Yeah. Oh, interesting. Well, is there a function you'd like to see in this?
Well, what I always like to do is I like taking a look at trig functions, but with a little bit of a twist sometimes. Like we can do cosine of 2 times e to the x.
Wow.
And what's fun about these guys is, let's see if it renders correctly. We'll see if this works. Again, this is all on the fly demos. We'll see what happens here. Oh dear.
Whoa.
And so now this is kind of fun, for at least the way I think about it. On the one hand, did I screw up the function? Cosine of 2 times e to the x. Oops. Yeah, cosine of 2 times e to the x. Does this make sense?
Yeah. Well, what we're seeing are the slopes, right? So the
Yes.
function's not showing it up because
That's right.
it's going up to 200,000.
That's right.
So the slopes are getting crazy.
Yeah.
But the function itself would be down so close to the x-axis that we can't even see it.
Yeah. And this is why it's kind of fun, because we know that cosine of blah should be bound between -1 and 1. But even this like benign interval that we chose, 0 to 4 pi, has proven to be problematic because we're going through so many different oscillations.
Yeah.
It doesn't know anymore. This function is just changing up and down so quickly, even though it's just bound between 0 and 1.
So what do you think would happen if we did the interval from just like 0 to 1 or 0 to 0.5?
Yeah, that's great. So 0 to 1. Let's try that one. All right. We're in somewhat sane land, but this doesn't capture a cosine quite well. But it sort of makes sense that it shouldn't, because you have that e to the x in there. That's just allowing this oscillation. You're just running through periods very quickly.
Mm-hmm.
But what's also nice though is, it doesn't even matter if you didn't know that this was a cosine of 2x. What you do know is that it's a cosine function, and at the end of the day, you're given this blue curve, and we're trying to figure out, well, how is this blue curve changing? We know it's decreasing, then it flattens out, and then it starts increasing again.
Mm-hmm.
And so if we look at this brown curve, we'll see that, well, that difference quotient, right, is negative. but it starts to increase away towards zero because this rate is slowing down. And where this function bottoms out is where this difference quotient goes to zero. And now the function is increasing again. And that's what these positive values here mean.
Oh, so I was at first I was surprised how high. Like it doesn't look like the slope should be 4 at that point.
Right.
But then I noticed that like in only kind of changing 2/10, like from 0.6 to 0.8, it went up almost a whole value.
Yeah,
Right. So it's actually, if we think about that as a rate, right? So it went up 1 and 0.2, that would be like 5 and 1.
that's right. That's right. Yeah, so it does capture, like, I mean, that is the purpose of these difference quotients, is to capture that rate of change.
Yeah. All right. So if I'm being too needy, let me know.
Oh,
But yeah, I would love to see it on a slightly bigger interval.
yeah, no, not needy at all. This is sort of the nice thing about having like a program that you can just kind of fiddle around with. So we can go to 0 to 2 if that helps, and see what happens.
Oh, nice.
So yeah, now this is interesting because, I mean, the function is decreasing, therefore these rates are negative, and then here's where it flattened out, so this rate is 0 instantaneously, so the function isn't changing right at that moment. And then from wherever this is, maybe 3/8, all the way out to here, 1 and I don't know, an eighth. The function is increasing, but we can see that the rate at which it's increasing starts to slow down, and then eventually the function turns away and starts to decrease.
Yeah, very, very interesting.
But because there's a cosine in here, there's this periodicity that the e to the x argument inside is making things go faster and faster.
Hmm.
So this behavior is starting to become more and more wild.
Because even though it's just going back and forth between 1 and -1, it's doing it in a shorter and shorter time.
Yeah. So if we were to take a look at something like even just the interval from 3 to 4, and for the time being, let's just actually not take a look at what these difference quotients look like. Let's just take a look at what this function looks like. So this is, I took away the derivatives, and I'm just looking at our function of interest. And
so yeah, well, I was just trying to think, what must those slopes be like? So in like in 200ths, it's going from -1 to 1. So even by that point, right? So
right.
that's got to be like a slope of almost 100.
Yep. Yeah. So this is, maybe, that's right. Like there are multiple movements from -1 to 1 just within 3.8 to 4. So if you imagine, and which it's not true, but if you just imagine that we have 3 periods in here within 0.2, that's 0.06 width per period.
Yeah.
And it's moving a distance of 2. So 2 divided by 0.06 is, we're hitting what, 200 over 6, so 30, 35, something to that effect. But then just as quickly as it went up 35, it dropped by 35, a rate of 35. So that's why before we saw this cone that
which is a really interesting shape. Yeah. All right. Well, I want to be respectful of your time, but I know you mentioned that you also wrote a tangent line finding program.
Oh yeah. So yeah, we can certainly do this. Let's take a look at what that looks like. So there are some classical questions that are often asked in a calculus course, right? And one of these questions is, given a function f and an x coordinate, which we'll call this guy point x. We often are, the question is, what's the equation of the line tangent to my function at that particular point? So if we come back to this guy here, let's just take a look at something a little bit more tame in an interval that's a little bit more tame. Just for a moment. This is, and it's clearly not cosine of 2. It is. It's x squared. So here, often we're interested in, if I picked a point here and tried to draw a line that was parallel to the curve in some way, whatever parallel means. This is often what we're interested in terms of a tangent line. So there is a line that we call tangent, and we'd be interested in saying like, okay, I know that at this point, the slope, the instantaneous rate of change at this point is some value. And if I know it's some value, can I make a line that is tangent, having that slope that is equal to the rate of change instantaneously at that, on the curve there. And so to do this, the standard setup here is that we have y minus the point of interest equals m times x minus the point of interest. That's our equation of a line. I forget what this is called in class. Is this point slope form?
Point slope form, yeah.
Yeah. So in point slope form, you're given x0, which means if you know x0 and you know the function, you can always find y0 by substituting x0 into the function. Mm-hmm. Once you have those, then all we have to do is figure out what m is. And in the world of calculus, m is the slope, and the slope here is the derivative. So this function here doesn't necessarily compute a derivative the way we would do in a calculus course, which is by hand and saying like, okay, x squareds become 2x's and what have you. It's going to simply reuse that derivative function that I wrote above, dy dx, and take in the function, take in the step size, and then I will give it the points of interest, or the interval of interest. And then from this, I get back my slope, the 2 points, my x0 and y0, and then for convenience, I just give myself what the equation of the line is automatically. So this is finding a tangent line. And so we can do the same here, where we can pick a function like x squared. And maybe we want to know what the slope of the tangent line is at the value of x equals 2. Mm-hmm. And for convenience and simplicity, I'll just make an interval around that point, 1 unit before, 1 unit after. We'll have to sample that interval enough so that we can actually visualize the function well. And then over here is me running my find the tangent line function, but again, at various step sizes, just to get a sense of at what point do I get to my tangent line. So doing this, let's make sure that I've got it right. Again, demo runs, here we go. So what we can see here is, we've got a thick blue line that I made just to show what x squared looks like. This black dot is the point of interest where I want to know what my equation of the tangent line is. Mm-hmm. And then we have various lines that were drawn depending on the step size that we chose. So when I had a step size of 2, well, it had to sample the function at x equals 2 and then at x equals 4. And then it said, well, okay, at x equals 2, my value is 2. And at x equals 4, my value is 16. So 16 minus 4 is 12, and then 12 divided by 2 is my slope of 6. That's what the 6 here means.
Oh, nice. And so again, we see kind of that increasing accuracy. And it's interesting, even jumping from 1/10 to, what would that be, 100,000th?
Yeah.
Right? We really only gain an extra 1/10 of accuracy in the slope.
Yeah. And the result here is, dependent on the type of function that we have. X squared is nicely enough behaved that going from 1/10 to 1/100,000th, you get that one place of accuracy. But if you had a function that changed very steeply, very quickly, then even that movement of 1/10 could be horribly inaccurate.
That's true. That cosine of e to the x function, right?
Yeah.
That'd be disastrous.
Yeah. And that's actually like why I like to look at some of those really fast changing functions, because one thing I remember when I was taking my calculus courses, we never encountered those types of functions in a calculus course because they're very hard to work with, hard to visualize.
And if we're computing by hand,
it's a disaster. But now that you have this, you have tools at your disposal. I think you use Desmos and GeoGebra and Wolfram Alpha. All of these things I didn't have. You can muck around with this stuff and really get a sense of like, ooh, wow, that step size. Really, you have to think about it from a computational standpoint. From an analytic standpoint, yes, it's a limit and what have you that I understand you haven't gotten to yet. But
but the idea is kind of out there, right? Because we have that idea we want to kind of get small, but we just haven't formalized it.
Yeah. So we can see that, okay, well, at exactly this point, all right, we have our slope at exactly this point, which is 4. And the equation of the line, you can effectively say is y minus 4 equals 4 times x minus 2. But all of these others, I mean, the truth is, even this is a secant line. It's just a very, very, very short secant line. But depending on how big your step is, the estimate for the rate of change at exactly this point varies. And what we think is a tangent line given a step size of 2 is going to be a little bit different when that step size changes to
something appropriately small.
Yeah. I think that's the right way to say appropriately small. Yeah.
Well, I just can't thank you enough. This was so cool to kind of be able to see the computation happening, right? For things that we've been talking about, and we can kind of see the results of these computations when we're using Desmos, but that's different than kind of being able to see inside the code.
Yeah, so, it's fun. Yeah.
So I really appreciate that.
You're welcome. Can I show you one more thing? Is that okay?
Oh, yeah.
Yeah, so the other nice thing here is if we come back to this derivative calculation or this dy dx thing, we can also have fun functions like absolute value of x, right? Now this is kind of fun in a lot of other ways. And I'm going to go over the interval -2 to 2.
Okay.
Because we know absolute value of x should look like a v of sorts. And when we do this computationally, something fun happens in terms of why that step size matters.
Right.
Because right here, if we were able to zoom in even more, we would see that even this is not just a pure vertical line as we would expect it to be. But this is transitioning from a negative slope to a positive slope. And at exactly this point, we don't know what the slope is because it depends on which way we're looking at it.
Right. Because on the one side, it's positive, and on the other side, it's negative, but that's different than that usual like 0 we'd expect in between.
Yeah. And I like this because it helps understand the smoothness constraint or the smoothness quality that a derivative tells us about the function.
Yeah.
So
well, that's super cool. And
Yeah.
it's a very dramatic illustration of the step size.
Yeah. Yeah. It's fun.
Yeah.
So then when you throw this in with like, you put in something like x raised to the absolute value of cosine of x over an interval that would be from -2 to 2, this starts to become fun because you have these sudden changes that happen in the function.
Yeah. Yeah, it's really interesting. And even after we learn some rules, right, that kind of thing is going to be tricky to evaluate.
Yes.
Yeah.
Yep. So
Oh,
yeah, you have to pay attention to the domain. You have to make sure that you're looking at it from the left, or you're looking at it from the right, or you're looking at it from both directions. And I think this is all the stuff that you're going to get to eventually, right?
yeah.
Yeah. So
Excellent.
yeah, anyway, that was the last fun thing I wanted to share.
Well, what a great note to end on. Manan, thank you again. I'll include links to your blog and other materials so that if the students are interested, they can see kind of some of the other stuff you do for fun on the side
Yeah.
besides your serious work.
Yeah. Sounds good. Thanks
Excellent.
for having me.
Oh, again, just thank you a ton.